Okay, so what we're going to look at are properties of nuclear radiation. Okay, so you will have heard radioactivity discussed before. Radioactivity occurs when there are changes in a nucleus. Radioactivity, okay, radio refers to a radius, okay, so for example, a radiator, something that's radiating is emanating from a centre, okay. Activity specifically counts per second and has the unit of becquerels or BQ for short. So these are counts per second that are being emanated from as a radius out. Okay, so in terms of nuclear radiation, we should be familiar with alpha already. So that is represented with a nucleon number 4 and an atomic number of 2. Of course, it's not an element. This is measured in U, which is the atomic mass unit, which is 1.66 times 10 to the minus 24 kilograms, which is approximately the same mass value as a proton and a neutron, although later on we will have a look and see that they are slightly different. Okay, in terms of this is a charge of +2, because it's the same as a helium nucleus, doesn't have the electrons around the outside, and it's highly ionizing. So that means that, as it moves through the air in its very, very short range, the positives can pull off the electrons of neighbouring atoms, and it does that with a highly ionizing effect. For every millimetre in air that it travels through, it will cause approximately 10,000 ions. In terms of beta radiation, beta negative is the emission of what appears to be a fast-moving electron. So, what you need to appreciate is that's coming from the nuclear centre. Okay, so a neutron changes into a proton via the weak interaction, which is W negative, and then that produces a beta negative decay as alongside an antineutrino. The antineutrino is important. Okay, this has got a baryon number of 1, this has got a baryon number of 1, these both are baryons, so 1 and 1 makes that balance. This has a lepton number of 1, this has a lepton number of -1 to cancel each other out, because there are no leptons on the other side. What is actually happening, the neutron has the quark configuration up, down, down, and the proton has the quark configuration up, up, down. The down quark is changing into an up quark. Okay, so in terms of beta positive or a positron does not knock around for all that long because of annihilation with other electrons, so it doesn't stick around for too long. This is happening where the proton changes into the neutron in the nucleus. Beta positive is released alongside a neutrino, and that is a W positive boson that is the exchange particle. Splitting that up can simply be written as that. Gamma travels at the speed of light because it is an electromagnetic wave, okay, and what that does, it reduces the amount of energy inside the nucleus by emitting that energy out into the surroundings. Neutron radiation happens where there are proton-rich nuclei and it releases a neutron and a proton. A neutron and a neutrino, do accept my apologies. So what happens is the electron is captured by the proton-rich nucleus, okay, leaving a neutron and a neutrino to be released. Feel free to test your knowledge on lepton and baryon numbers by testing that out. Right, all of these are detectable by a GM tube, which stands for Geiger-Müller tube, okay? Now, a Geiger counter detects the amount of ions that are produced per millimetre. The front is made from a thin film known as the material mica, okay? All of these types of radiation can penetrate through the mica. Although what I will say is that it does introduce an element of uncertainty because in some cases the mica is absorbed. The other thing to take into account is, for recalibration purposes, there is a dead time, okay? It will not intercept all the ions every single nanosecond. There is a dead time in each, so there may be gaps where it's not taking a reading if you are bombarding it with a lot of ions all at once. The other thing to take into account is the background radiation must be subtracted. Okay, so we've got alpha, beta, and gamma, and neutrons. Alpha has a short range in air, okay, a few centimetres, and can be absorbed by paper. Beta has a range in air about 1 metre and can be absorbed by aluminium. And gamma has an unlimited range in air and follows an inverse square law and is absorbed by thick concrete or lead. Okay, in terms of the ionisation, if alpha is ingested, that is in the body, okay, until it is passed out of the body, until it is excreted, that high ionisation may cause mutations of cells inside the body and lead to cancers. If it's not ingested and alpha is placed on the skin, it will cause severe skin burns due to the ionisation. Beta can pass through the skin, okay, still has ionising properties but not as strong as alpha. And gamma can penetrate all the way through the body, still has slight ionising properties, okay, so that's why we see it used in medicine to treat various different illnesses, okay, and those are the different properties of nuclear radiation. Thank you.